In this video, we're going to be talking about Riemann sums and something called the definite integral. So in the last section, when we talked about left, right, and midpoint rectangular approximation methods, those were all examples of Riemann sums. And these were used to help us estimate area under the curve, and we used rectangles. So we have this summation notation. The Riemann sum is a sigma notation, where n represents the number of subintervals. So you can see the number of subintervals up here. Basically, it's representing the sum of all of our rectangles. So f of x sub I, this just represents the height of our function at some point in our subinterval, and then delta x represents the width of our subinterval. And so this is really just a sum of the number of rectangles that exist in our subinterval, where this represents their area in here, because it's the height of the function, or the height of the rectangle times its width. Now this leads us into the definition of something called a definite integral. A definite integral is defined on the interval from a to b, and we use this notation, the same notation that we used for an indefinite integral, but really what it represents is the limit as n approaches infinity of the sum of all of these rectangles. Now, basically what's happening here is we have a situation like this. We're trying to estimate this exact area under the curve. And if we want to find the exact area, basically what we're doing is we're trying to make the change in x really, really small. We're trying to increase the number of subintervals to be infinite, right? So it's a limit as the number of subintervals goes to infinity. So essentially what that's going to do is it's going to make the width of our subinterval infinitely small. And that's what's going to give us this kind of smooth curve under here, where we have this area that's not just a bunch of rectangles, that's missing some values, right? So the Riemann sum approximation is exactly that. It's an approximation of the area under the curve. But the integral, which is the limit as n goes to infinity, represents the exact value of the area under the curve, given that this function is positive. Because in the situation where we have a function, if the function lies below the x-axis, we actually have some negative areas that we're dealing with here. So if you have a function that is continuous, then that implies that it is integrable, right? So say that 10 times fast. A function is continuous on a closed interval from a to b, then f is integrable on that same interval. And basically that means that the definite integral on that interval would exist, right? So just quickly going back, when we're talking about the definite integral, the interval here is what determines our upper and lower limits of integration. So a and b, these are called the limits of integration, and it's determined by our interval on which we are taking the integral. So b is the upper limit, a is the lower limit. We still have our integrand and variable of integration here. Now this x sub I just represents the height of our function at some point inside our subinterval, and it's going to depend on where we're taking the approximation. So in this case, we have a midpoint approximation. If we were doing left endpoint or right endpoint, that would be the value of x sub I there. Okay, so the first example that we're asked to do is express this given limit as a definite integral. So we want it to be the integral from a to b of some function times our variable of integration. Now, because it's a delta x here, that tells us that we are going to be dealing with dx, right? So our variable of integration is going to be x. So delta x is essentially just the same as dx. Now this piece here is really just our function where we replace x sub I with x. Right? We replace x sub I with x in our function, and that's essentially what we have here. So it's going to be an integral from, now remember we said that the interval determines our limits of integration, so it's from 0 to pi, and our function is going to be this whole thing here, so it's going to be x cubed plus x times the sine of x, and then this whole thing times our differential of x, which is determining the variable in which we are integrating with respect to. So this whole thing, as crazy as it looks, is really just as simple as rewriting it, replacing x sub i's with x. The delta x becomes our differential of x, And this whole limit of the sums is basically what we're denoting here. And it's over this interval from 0 to pi. And that would be how you would write this summation notation in integral notation. Okay, so when we're defining a definite integral and we're talking about the area, the definite integral actually represents something called the net area. So basically, you can have positive and negative areas, and the reason why an area would be positive versus negative is all based on its location in the graph relative to the x-axis. So if you have a function, when your function is above the x-axis, the area under the curve there is positive, right? You can see that there. And when your function is below the x-axis, the area under the curve in that area would be negative. So one thing to note is that your net area does not have to be positive. You can have a negative net area, and your net area could be less than the total area. When we talk about total area, basically the total area is where you take the absolute value of the area under the curve. So anything that is positive stays positive, but then anything that is negative, you take just its value rather than the sign of it, because you want to know actually how much a total accumulated area lies under the curve for some interval. So that's total area is a little bit different from net area. Net area is just represented by our typical integral, right? So the integral from a to b of f of x dx represents the net area. If we wanted to find total area, we would take the absolute value of our function here. So when we're looking at area under a curve, there's a couple ways that we want to can think about this, right? So the area from a to b of our function is going to be just equal to the integral on that interval if our function is positive, right? Now, if our function is negative, because the area itself, when we're talking about area, we're talking about just like the unsigned area, not talking about it being positive or negative. So if the function lies below the curve, then the actual area that is represented between the curve and the x-axis would be the opposite of the value of the definite integral. So this is our unsigned area, right? We're not talking about it being positive or negative. It's just going to be the value of the area under the curve. And so if our function lies below the x-axis, then we would have to take the opposite of the integral from a to b of our function. So let's go ahead and try and evaluate some integrals and find the value of the area under the curve using geometry, because we don't quite have a method yet to actually calculate the area using the integral. So we're going to use geometry. So first thing we need to do is graph our function. So let's go ahead and draw some axes here. So we're graphing this function on the interval from, you can see here, from -1 to 2. And the function itself, this is f, remember, is just y equals 7. So we have a horizontal line here, just like this. And it goes from -1 to 2. So what we want to do right now is we want to calculate the area under this curve here. Right, so that's what we want, is this area that's in blue. So this area from, right, we're going from -1 here to 2. Jeez. And we want to find the area. So in this case, we're just looking at the area of a rectangle, right? And we know that the area of a rectangle is equal to the base times the height. So the base is the distance from -1 to 2, which is 3. And our height is the value of our function, right? We know it's at y equals 7, so that's going to be 21 square units, right? So that would be the integral here would be equal to 21. Okay, so let's try another example. So in this case, we want to draw the line 3x minus 6, and we're trying to calculate the area under the curve from x equals 2 to x equals 5. So again, draw some axes here. And we have our curve. Let's go like this. So it has a slope of 3. It intersects the y-axis at -6. So it's going to do something like this. So down here is -6. It's going to intersect the x-axis. So the x-axis is when y is 0. So that's going to be at 2. And that's where we're starting. and we're going to graph it up to 5 here, up to 5. So we're trying to get this area here from 2 to 5. So this area here in blue is just going to be represented by the area of a triangle. And we know the area of a triangle is 1/2 times the base times the height. So in this case, the base is 3. So it's 1/2 3. And then the height. So we need to figure out what is the value of our function when x is equal to 5. So this has a coordinate of 5, comma. So plugging in 5, 3 times 5 is 15, minus 6 is 9. So the height is going to be 9 there. So it's 27 divided by 2. So that is going to be the area. All right. So in this example, we have a semicircle, actually. This is the, right, because if it was y equals this, then if we squared both sides, we'd get y squared equals 4 minus x squared. We could add x squared, and that would be a circle. And this is just going to be a semicircle because it represents 1/2. So that's actually going to be the top half of a semicircle. So, and it has a radius of 2, right? Because that's the value of r squared is 4. So when we're looking at this one here, we can go ahead and draw our circle. So let's draw our circle here. And we only care about the top half. Whoops. We only care about the top half here. Let me draw this again. We'll put this right here. We want this area here. Right? So it's only the area of the top half of the semicircle from -2 to 2. All right. So what is the area of a semicircle? Well, we know the area of a circle is pi r squared, and it's a semicircle, so it's half of that. So it's 1/2 pi r squared. So in this case, the radius is 2, so that's going to be 1/2 pi times 2 squared, which is 4 pi over 2, which is just going to be 2 pi. So this has an area of 2 pi. Next, let's look at some properties of definite integrals. So there are these 5 properties. We've actually seen 2 of these before. We've seen the constant multiple, and we've seen the sum and difference properties with indefinite integrals. The only difference is now we have limits of integration here. So the first thing that is important to note is that the order in which we list our limits of integration matter, right? So if I have my integral from b to, this is b to a, right? If I have it from b to a, then that integral is equal to the opposite of the integral from a to b. So basically what you're doing is you're going in the opposite direction. So you're starting at your right endpoint and you're moving to your left endpoint in this case. So because you're accumulating area backwards, that area is actually going to be the opposite of the area in the other direction. So integrals also have a directional component to them. Now, if you're taking the area from a to a, your limits of integration are the same. Basically, there's no actual interval that you're integrating. Then you've accumulated no area, right? So area under a curve or an integral in a definite integral is an accumulation of area. So if you aren't moving anywhere from where you start, then you've accumulated no area under your curve. So again, the constant multiple rule means we can just pull a constant out of our definite integral, just like with an indefinite integral. Same with a negative, because it's like a -1. Sum and difference still applies, right? So if you have a sum or difference of 2 functions inside a definite integral, you can break it up into a sum or difference of 2 integrals with the same limits of integration. Now, this additivity property is an interesting one because it says if you have a function integrated from a to b plus from b to c, right? So notice that the upper limit is the same as the lower limit here. Then that's equal to the integral from a to c. So if you have interior upper and lower limits in a sum or difference that are equal and the function is the same, then basically you can combine these to be just the integral from a to c. Now, this is also true in the other direction, and we will use this frequently in the other direction, especially if one interval, this one is, let's say, negative and this one is positive. So we'll need to like split it there if we're trying to calculate something like the total area. So let's go ahead and use properties of integrals to evaluate this. Now, one thing to note in this example is we can see that the upper and lower limits of integration are the same. So that automatically tells us this area is 0. Okay. So in this case, we want to find the area under the curve from 2 to negative 2. So notice, normally when you're writing an integral, it goes from the smaller number to the larger number. So this one is switched, which means we're probably going to be using the one where we take the opposite. So take the opposite of, from negative 2 to positive 2, of 2 minus x with respect to x. Okay. Now, we could also, if we wanted, take this negative and distribute it through. Because we have that constant, the constant multiple property, it also can be put back into your integral. So if you wanted to deal with a line that didn't have negative slope, you could do it that way. So we could say this is also the same as the integral from negative 2 to positive 2. Distributing through, that would give us x minus 2 with respect to x. Okay, so if we want to find this area, we can just draw our equation here. So let's go ahead and draw some axes and graph this line. Okay, so it has a y-intercept of negative 2. It has a slope of 1. So it's going to look something like this here. Right, so this is our line. And we are trying to calculate the area under the curve for going from negative 2 here. So over here at negative 2 up to positive 2 here. So this is the area that we're trying to go and figure out. So we're going here from negative 2 to positive 2. This is just a triangle, right? So the area is going to be 1/2 the base times the height. The base here is this measure here. So from negative 2 to 2, that is 4 units. And then my height, so if I plug in negative 2 into this, negative 2 minus 2 is negative 4, which means the height here is 4. So that's going to be 1/2 of 16, which is 8. Now, one thing to note, though, is this value should be negative, right? The area should be negative. So the area is actually going to be negative 8 because it's below the x-axis. So it's below the x-axis, so its area is actually going to be negative, right? So that area is negative there. So now we want to integrate so we have an absolute value. It's been shifted left 3 units, and we want to go from negative 5 to 0. So we can look at this way. So it's going to sit on the x-axis, but it's going from negative 3 like that, right? It has its vertex kind of like this. And we want to calculate the area from here at negative 5 to here at 0. So it's going to be a couple triangles. So basically this is going to be, from the properties, it's going to be the same as the integral from negative 5 up to 3, or sorry, negative 3 of our function, absolute value of x plus 3 with respect to x, plus the integral from negative 3 to 0 of the absolute value of x plus 3 with respect to x. And we could probably rewrite these because we can redefine the absolute value as a piecewise function, and we know for values of x less than negative 3, it's going to be the opposite value. So it's going to be 3 minus x here. So we could rewrite it like that. 3 minus x, or negative x plus 3. And then for values of x to the right of negative 3, it's going to just be this x plus 3 here. So it would be like that. So we can call this, let's call this area 1. We'll call this one area 2. All right, and so this is equal to, that's going to be area 1, and that's going to be area 2. And we're adding these together. So it's 2 triangles. So 1/2, so area 1, its area is 1/2 the base. The base in this case is 2 times the height. So at negative 5, if we plug this in, negative 5 plus 3 is absolute value of negative 2, so that's 2 there. So negative 5 comma 2. So its height is 2. And then area 2, its measure of its base is 3. So it's 1/2 3 times, if I plug in 0, the absolute value of 3 is 3. And so that's going to be, so half of 4 is 2, half of 9 is 9/2, which is 4.5. So this whole thing has an area of 6.5 units. 6.5 units there. All right. And then this last one. So we're going from -2 to 3. Now we probably want to rewrite this, right? So the absolute value of x, we know divided by x can be redefined to be 1 for values of x less than 0, or sorry, -1 for values of x less than 0, and +1 for values of x greater than 0. Because when x is less than 0, this is equal to its opposite, so we get -x over x, which is -1. When x is greater than 0, it's equal to itself, so we get x over x, which is 1. So if you were to graph the graph of this, it looks something like this here. So we'll have a horizontal line here, and then we have this other horizontal, whoops, sorry, that's switched. It's like this, horizontal line here, and then we have this horizontal line like this. And so the area that we're trying to calculate is from -2 here up to 3 here. Okay, so that's going to be like this area here, and then this area here, and it's going to be the sum of those two. Now in this case, this we'll call a sub 1, and this we'll call a sub 2. Now in this case, a sub 1 is going to be negative, right? It's below the x-axis, so it's negative. So a sub 1 is equal to the height here. This is at -1. This is at +1. The height here is 1, right? Its height is 1. Its width, its base is 2. So the measure is 2. But remember, it's going to be negative because it's below the x-axis. And then a sub 2, its measure is going to be, its height is 1, and its base is 3 units. And so it's going to be 3. So a sub 2 plus a sub 1 is going to be -2 plus 3, which is going to be 1 unit. So this whole thing just has a net area of 1. So in this example, we're asked to evaluate this integral, and we're given the information, about the values of the area under these separate curves from 2 to 4. So first thing that I'm going to do is I can actually break this up because of the sum and difference properties. So I'm going to separate this into 3 different integrals. So we can say that this is equal to the integral from 2 to 4 of x cubed dx, dx, minus the integral from 2 to 4 of 3x dx, and then plus the integral from 2 to 4 of 7 dx. Okay, so now how can we use this information here to help us evaluate this? Well, this first piece here is exactly what we have right there. So I actually know that this first chunk there is just 60. Okay, now this second piece, right, this piece right here that we have in this part there is just going to be equal to this middle piece times -3, right? It's because it's 3x, so that's going to be 3 times that. Because remember, we could take this 3 and pull it out. So it's essentially going to be -3 times the integral of x dx. So that's going to be -3 times the value of this piece here, which is 6. And then this, notice there's nothing really written in as our integrand. So really we could think of it as being a 1 times dx. So this 7 times dx, basically we could pull the 7 out and it'd be 7 times the integral from 2 to 4 of dx. So it's just 7 times this piece here. So it's plus 7 times 2. So we can then use all of that information to help us evaluate this. So that's 60 minus 18 plus 14. -18 and 14, that's -4. So 60 minus 4 is 56. So this whole thing has a value of 56 units. Next, we're going to be talking about something called the trapezoidal rule. So trapezoidal rule is similar to rectangular approximation, except now we're using trapezoids instead of rectangles to estimate the area under our curve for our certain subintervals. This gives us a little bit more flexibility because we're not then restricted to strictly rectangles, and so we don't necessarily get as much overestimate or underestimate as we would if we were using right or left hand rectangular approximation. So to approximate an integral from a to b, we can use this equation here. So this kind of long equation is what we're going to use for trapezoidal rule. And I'll talk about what all the different parts represent here in just a second. But it's where we take our interval from a to b, partition it into n subintervals with equal length. And our length is found in the same way that we did before. We take the measurement of our interval, so you do b minus a divided by the number of subintervals, and that's going to give us actually the height of our trapezoids, right? Because if you look at our trapezoids here, right, they have their parallel bases like this, and then their height is represented by the width of our subinterval there. So that's going to be how we're determining the height of our trapezoids. Now, all of these pieces are basically just the y values at the specific endpoints of our subintervals. So y sub 0 is the y value at our first endpoint. So it's the left endpoint. And then y sub 1 is the y value at our second value in our interval. Now, the reason why y sub 1 shows up twice is because it's accounted for in not just this trapezoid, but also this trapezoid, right? So you can see that the y sub 1 in here, this value here, gets accounted for twice because it's used in two of our trapezoids. And so all of the interior measures, right, everything in the inside of your subinterval, all of those interior heights are being counted twice because they're included as parts of two trapezoids, right? The endpoints, right, y sub 0 and then ultimately y sub n, they're only counted once because they only exist in this one trapezoid here. So this is basically the trapezoidal rule. One thing that you can also do is you could do the left rectangular approximation and the right rectangular approximation, and you could find their average. And the average of the left rectangular approximation and the right rectangular approximation is actually going to be equivalent to your trapezoidal approximation using trapezoidal rule. So basically, we can informally say that trapezoidal rule is essentially using trapezoids to approximate the integral by basically just adding up the area of all of our trapezoids. And remember, when you're doing this, the area of a trapezoid is 1/2 the height times base sub 1 plus base 2, right? Base 1 plus base 2. And we're getting all of that in this rule here. It's our height divided by 2, and then this is base 1 and this is base 2. But then remember, this second base is also included in other trapezoids, and so that's why we end up with this like this. So let's go ahead and get into an example here, and we want to use trapezoidal rule to estimate the area from 1 to 2, right? So we're going from 1 to 2 here. We're going to estimate the area under this curve of our function x cubed. So in this case, we have the function y is equal to x cubed. We're told we're using 4 subintervals. So the change in x, right, or the height, we'll call this, change in x is the same as the height, which is going to be equal to b minus a. So we're going from 2 to 1. So 2 minus 1 divided by 4. So our heights for our rectangles are going to be 1/4. All right. So using trapezoidal rule, so t sub 4, the sub 4 is basically just telling us it's trapezoidal rule about 4 subintervals. So it's going to be 1/2 times the height, which is 1/4, times what? Okay, so first let's go ahead and draw our trapezoids. So I have this trapezoid already drawn here. So this one fits here. Let's go ahead and make it fit right. And then let's go ahead and fill in the rest of our trapezoids here. So we can make another trapezoid. We can adjust the height here so it hits there, and then it's going to hit here. So you can see that trapezoidal rule is kind of nice because like I said, we aren't restricted to just using rectangles. So we can actually get pretty close in our approximation for this here. So let me just use these to kind of try and draw the rest of my trapezoids here. So here we are. And last one is here. Is our last little trapezoid. Okay? All right. So remember, it's 1/2 times the height times the y value of our left endpoint, and then twice the y value of all of our interior endpoints. So our interior endpoints are going to be here, here, and here. Right here, here, and here. So those are going to be 2 times their y value. And then at our left endpoint, it's going to be the y value of this and the y value of this. Now we know that the height, right, the change in this piece right here is 1/4. So that means this is 5/4. This is 6/4 or 3/2. And then this is 7/4 there. So that's what we're dealing with in this. Okay? All right. So it's 1/2 the height times the y value at 1. So that's going to be 1 cubed plus twice the y value at the second subinterval endpoint. So that's going to be 5/4 cubed. And it's being cubed because remember that's the value of our function is y cubed. So we're cubing the x coordinate there. Plus 2 times this one here, which is 3/2 cubed. Plus, let me move this over just a tad bit. Give us a little bit more space. Plus 2 times this one, which is 7/4 cubed, plus, in this case, it's 2 cubed. And we're going to multiply all of that here to give us our approximation using the trapezoidal rule. Okay, so what does that equal to? Well, that's going to be 1/8, right? Because 1/4 times 1/2 is 1/8. Times, if you plugged all this stuff into your calculator, you would get that is 30.375, which when you simplify this ends up being 3.797 rounded to 3 decimal places.